Hey everyone, Houston Math Prep here talking to you about improper integrals. A definite integral from a to b fx dx is improper if it has an infinite bound. Either the lower bound is negative infinity or the upper bound is positive infinity, or if it's both, that's certainly improper as well. Also, if it has an infinite discontinuity on the interval. Okay, so it has basically a vertical asymptote either at A or at B or somewhere in between, then it will be considered an improper integral, and we'll have to look at doing something a little bit different. Anything where an integral involves an infinity, infinity is not a real number we can just plug in and do arithmetic with our bounds. We're going to have a little bit different process when we have something like this. Here we have some examples of improper integrals where you can see there's an infinite bound. I have an integral from 2 to infinity. Here and here will work both of these. I have a negative infinity as a lower bound, and then I have a doubly improper integral. I have both a negative infinite and a positive infinite bound. So let's take a look at some of these improper integrals with infinite bounds. So if I have an integral from a to infinity, where I have a positive infinite upper bound, then I will basically sub in some sort of a dummy variable for my upper bound and simply take the limit as that thing goes to infinity. So the idea again is I can't plug infinity in and do arithmetic f of infinity minus f of a. So I plug in f of something and I imagine what happens as that thing gets really large as it tends toward infinity. Also, if we have a negative infinite bound, we'll do the same thing. We'll sub in a dummy variable for the lower bound and consider what happens as that goes more and more negative toward negative infinity. Of course, we'll assume that the function is continuous on the interval that we are trying to find this definite integral. If it's the case where we have a doubly improper integral, I have both a negative infinite bound and a positive infinite bound. In other words, we are integrating the function over the entire real number line. Then what we will need to do is split the integral into two separate integrals at some real number. So I'll need to pick some value, say c, in between the negative infinity and positive infinity, and split my integrals from negative infinity to c, which will be improper itself because the negative infinity will still be improper. So we'll sub in something for our negative infinity and take the limit as that thing goes toward negative infinity. And then we'll also have an integral from c to our positive infinity. In that case, plugging in a dummy variable here and letting that dummy variable tend toward positive infinity. Okay, the most common thing that people will split an integral at is 0, but it'll sort of depend on the expression that you're integrating and what is easiest maybe to plug in and evaluate in your opinion. Let's go ahead and work through our examples that we showed you before. We have the integral from 2 to infinity of 1 over x dx. So the first thing we'll do is we'll go ahead and substitute some dummy variable in our bound. So we'll go ahead and say from 2 to b, and then I'll go ahead and say limit as b approaches infinity here. That will be the limit of the same integral. So that will become the limit as b approaches infinity of my antiderivative ln absolute value of x evaluated from 2 to b. And remember, we're letting b tend toward infinity. So we'll go ahead and plug in our bounds. That will be the limit as b approaches infinity of ln of b minus ln of 2. So the first thing maybe that we might notice is that ln of 2 is just going to be some number. So in other words, whether or not we get a real number for this answer is going to depend on this. And so we say, what happens as b gets larger and larger? And ln of x is one of those functions that if I plug in a bigger and bigger value, I will eventually become as large as I can possibly imagine. So we actually end up with something infinite here minus some real number, the ln of 2. So if I have an infinite amount of stuff here, subtracting off some real number is not going to change that. So we are going to tend toward positive infinity with this integral. In other words, we can also say that this integral diverges. It does not arrive at a real number. Looking at our next one, the integral from 2 to infinity of 1 over x cubed dx. So a similar substitution here. I am improper because of this infinite bound here, so I will instead think of the limit from 2 to b and let b become infinitely large. And the antiderivative of 1 over x cubed will not be a log rule anymore, that will be a power rule. So we'll have the limit as b approaches infinity. This we can think of as x to the minus 3. So our antiderivative, we will have the power go up by 1. X to the minus 2 will divide by that new power, so that would be negative 1/2. And we'll evaluate from 2 to b. Okay, let's go ahead and plug in our bounds and then think about the limit as b gets really, really big here. So this x to the minus 2, that'll really be on the bottom, right? So it'll be 1 over 2b squared minus negative 1 over 2 times, and then if I have x squared on the bottom and I plug in 2, that will give me 4. So let's look at this first term here. As b gets really large, the bottom of this fraction is going to get really large, so this fraction is going to approach 0. So we will get 0 minus a negative would be plus, and then we'll have 2 times 4 there, and so our limit of this first term being 0 leads us to a real number of 1 over 8. So we would say that this integral converges because we got a real number answer. Okay, here we have from negative infinity to 0 the integral of e to the 2x dx. So this is improper here, our lower bound this time. So I will go ahead and think of maybe plugging in a here. So I'll go from a to 0 and I'll look at the limit as a approaches negative infinity. We'll have the limit of that integral there with those bounds. And we will now go ahead and integrate. So we'll have the limit as a approaches negative infinity. The antiderivative of e to the 2x is going to be 1/2 e to the 2x. And we'll evaluate from a to 0 and take the limit as a approaches negative infinity. Okay, let's go ahead and write that down. So we'll have the limit as a approaches negative infinity of the following things. So if I plug in 0, I will get 1/2 e to the 0 minus 1/2 e to the 2a. Okay, so notice that there is no a in the first term, so 1/2 times e to the 0 would be 1/2 times 1, so that's just 1/2. Now our limit applies here because we have an a. If a tends toward a really, really big negative number, then this will be a really, really big negative exponent. Okay, so what we'll actually have is not exponential growth, but because this exponential has a negative exponent, it will be an exponential with a really large exponent in the bottom. This is not actually saying e to the infinity, because again, we can't plug in infinity and do arithmetic with it, but e to some really large exponent on the bottom of the fraction means that now this fraction is going to tend toward 0. So we will actually have 1/2 minus something that gets really close to 0, which will just give us 1/2. This one also converges. Next, we have the integral from negative infinity to positive infinity, 1 over 1 plus x squared dx. I'm going to break this into 2 integrals. I'm going to go ahead and split it at 0. 0 is a pretty easy place to break something up, so I'm going to say from negative infinity to 0, this integral, plus, then we'll go ahead and have the rest of it, so from 0 to positive infinity. So we've just broken this up into 2 separate pieces. Now both of these pieces are still improper, yes? So if we look at what we have here, we would have the limit let's say from a to 0, as a approaches negative infinity for this first one here, dx over 1 plus x squared. And then we will also have a limit, and this one will go from 0 to infinity. Let's make that 0 to b, and so for this one I'll say as b approaches infinity of the same expression. Now you only have to do this integral once, right? These are the same antiderivatives, so once you figure it out one time, you've got both of them. So we will hopefully recognize this as an inverse tangent rule. So this will be the limit as a approaches negative infinity of the inverse tangent of x, evaluated from a to 0, and then we will add to it the limit as b approaches infinity of the same antiderivative, inverse tangent of x, evaluated from 0 to b. Now, if you are having a hard time thinking about these limits on the inverse tangent function, we have gone ahead and provided you a graph of the inverse tangent function here. So let's go ahead and plug all of these things in. So we will have the limit as a approaches negative infinity of the inverse tangent of 0 minus the inverse tangent of a, and then we will add to it the limit as b approaches positive infinity of the inverse tangent of b minus the inverse tangent of 0. Okay, so let's use our graph here to hopefully tell us what's going on. So first we need the inverse tan of 0 has nothing to do with our limit here because there is no a. So the inverse tangent of 0 is actually 0. So we get 0 there. Minus, and then the inverse tangent of a. So as I approach negative infinity on this graph, in other words, if I go to the left, what y value am I approaching as I go farther and farther out? It has a horizontal asymptote. This is at y equals negative pi over 2. So that is the limit for this one. So that's actually negative pi over 2 for that limit. And then our second limit, so we have limit as b approaches infinity, inverse tangent of b. So as we go to the right forever on this graph, what y value are we getting close to? The answer is positive pi over 2. So this first limit here is positive pi over 2. The limit as b approaches infinity does not affect the second term because there's no b. Inverse tangent of 0 again is going to be 0. Because the graph goes through the origin there. And now we have our answers here, I think. So we have negative pi over 2, also known as positive pi over 2, plus another positive pi over 2, and that will give us an answer of pi for this integral. So this integral converges also. Okay, let's go ahead and take a look at two integrals that maybe when you first look at them seem like proper normal integrals, but they're actually improper integrals based on discontinuities. So if you notice, the function 1 over x squared would actually have an infinite discontinuity, a vertical asymptote at x equals 0. We are actually improper because of the bound x equals 0 there. If you look at this one over here, think about dividing by 0 would give us a vertical asymptote here as well. That would be when the bottom is 0, and that would be when we have 4 minus 4 in the root. So actually this x equals 4 is what makes this integral an improper integral. We'd have a vertical asymptote at x equals 4. Just some quick things to note here. If you have an infinite discontinuity at, let's say, your upper bound, then you'll need to replace your upper bound with something else, some dummy variable, and let your dummy variable approach b from the negative side. If you think about the integral a to b, and if I'm in between a and b, I can only approach b from below, from less than b. So that's why we'll use a one-sided limit as we approach b from the negative side. If you have an infinite discontinuity at a, in other words, your lower bound, then you'll need to put in a dummy variable for your lower bound and let that dummy variable approach a from the positive direction. If you're in the interval between a and b and you want to approach a, if you're in this interval, you can only approach a from above a, right? From the positive side of a. So that's why we'll have a one-sided limit there. If your function has an infinite discontinuity in the middle of the interval, then you'll have to split the interval into two, like we did when we had a doubly improper integral over the whole number line from negative infinity to positive infinity. Let's look at these two examples that we showed earlier. So we have the integral from 0 to 2, 1 over x squared dx, and we noted that this was improper, the 0 here, because there's an infinite discontinuity there. So that will become a limit. We will need to replace our 0 with something. I'll just replace it with a, since a is usually on the bottom. So we'll say from a to 2, and I want a to approach 0. Now, if I'm on the interval 0 to 2, I can only approach 0 from one side, and that would be from the positive direction. So we're going to approach 0 only from the positive direction. And we'll still do this integral 1 over x squared dx. This will be a power rule. So we will have the limit as a approaches 0 from the positive side. This is x to the minus 2. So if I'm integrating, then my power goes up by 1, and I divide by the new power. So we get negative x to the minus 1. We'll rewrite that in a second, from a to 2. And we'll look at our limit as a approaches 0 from the positive side. Okay, let me go ahead and rewrite this. So this will be the limit as a approaches 0 from the positive direction of negative 1 over x from a to 2. Let's go ahead and write those separately now. So limit as a approaches 0 from the positive side. Plugging in 2 first, we'll have negative 1/2. And then we will have negative 1 over a, so minus negative 1 over a. So thinking about a being a smaller and smaller positive number does not affect the first term. So we would simply have a negative 1/2. And then if this a gets smaller and smaller, then we get 1 over a smaller and smaller number, and 1 starts to look enormous compared to this really small thing that we have that's close to 0. So we will actually get something infinitely large here. And if I have an infinite number added or subtracted with a real number, then of course that will tend toward an infinite number, and this integral will diverge. Let's look at our last example here. Again, we noticed before that 4 was going to make this improper, so we'll need to replace our 4. It's my upper bound. I'm going to go ahead and replace it with a b, so I'll say 0 to b, and I will let b approach 4. And if I'm on the interval 0 to 4, I can only approach 4 from the smaller than 4 direction, from the negative direction. And then we'll need to do the antiderivative of dx over root 4 minus x. So let's go ahead and do a u substitution here. We'll say u is 4 minus x, and du will be negative dx. So we'll go ahead and plug all that stuff in there. So we will still say the limit as b approaches 4 from the negative direction. You could go ahead and solve your new bounds. I'm going to go ahead and just leave these as x equals 0 and x equals b. And we'll do the integration, and then we'll sub back. So this will be a negative du over the square root of u. Okay, so we don't lose anybody. Let's go ahead and well, we could bump out the negative, and I'm going to go ahead and write my root u on the bottom as the negative 1/2 power of u. So that would be u to the negative 1/2 du. Again, these are still x bounds here, so x equals 0, x equals b. We'll take the limit as b goes to 4 from the negative side. Okay, let's go ahead and do our antiderivative. So we will have, I'm going to go ahead and Bump my negative outside the limit. I have negative limit b approaching 4 from the minus side. And then my antiderivative, my power goes up by 1, so that's u to the 1/2. Divide by the new power, 1/2 would be like multiply by 2. My bounds, remember, are x bounds, so I'll say x equals 0 and x equals b. Let's go ahead and replace now in terms of x, so I don't have to write this again. I'm going to go ahead and bump the 2 out as well. So let's say -2 times the limit as b approaches 4 from the minus side. U to the 1/2 would be my original substitution for u. So that will be the square root of 4 minus x. And now that we're back in terms of x, I can go ahead and just write these bounds as 0 and b. Let's drop our bounds in there and evaluate our limit. So -2 times my limit as b approaches 4 from the minus side of, so plugging in b, I would have square root 4 minus b, and then I would have minus the square root of 4 minus 0. Okay, our limit as b approaches 4 minus will only affect the first term because that's the only thing that has b in it. So in the root I would have square root of 4 minus something really close to 4 getting closer and closer to 4. So this would get closer and closer to 0 under the root. So we would have -2 square root of 0, and then here minus 4 minus 0 would be square root of 4 there. And doing some easy simplifying here, -2 times the square root of 0 would be 0 minus the square root of 4, which is 2. And -2 times -2 will give us +4. And this integral converges. Okay, hopefully that gives you plenty of examples of improper integrals to go off of. Good luck with your integrals determining if they're proper or improper. We'll see you in a future video.